For this video, I'll be going through chapter 19, Electromagnetic Induction, Success Criteria C. Now, sketch a graph of voltage output, against time for simple AC generator. Maybe we can do some quick recap. So the first thing that you need to know is that who are the three people involved: Faraday, Fleming, and Lenses. So you can either watch back success criteria A video or success criteria B. Then what was covered in success criteria B was that we were talking about simple AC generator. You need to know what are the some of the parts which we have actually a split ring. Sorry, not a split ring. It is a slip ring. And we have two slip rings actually, and we also have two carbon brushes. And what we need to know is that there will be induced current produced. When we provide a force to cause the conductor to turn in external magnetic field, because there will be a change in magnetic field experienced by the coil. And this change, according to Faraday's law, there will be induced current. And to take note that for the coil, the turning of the coil is one direction. Of course, you can turn it back the other direction, but usually we turn it in one direction. And the direction of current in the coil is also in one direction. What do I mean? So when I am looking at the coil, let's say the current will be flowing in this direction. But when it comes out, due to the how the slip ring is being connected, the direction of current in external circuit, the direction of current in external circuit will change every half a revolution of the coil. So this is important. The turning of the coil, we keep it consistent one direction, so that the direction of current flowing in the direction of current in coil is in one direction, but the direction of current in the external circuit will change every half a revolution, and this brings about the alternating current, AC current. So besides the direction change, there will also be a magnitude change. Let's see how this happens. So we are placing a coil in a magnetic field of external magnet. North here and south is here. So we are looking at it in this direction. So if A and because we are providing the turning effect, we are applying a force on the coil to make it turn in the clockwise direction. Therefore, AD will be up. AD will be up. The force on AD will be up, and the force on BC will be down. So if we apply right hand, Fleming right hand rule, we'll see that the current is actually, let's see, please use the correct hand, the right hand. The current will actually be going from A to D and B to and C to B. So it will be going from A to D and then C to B. So at this position, in position 1, the magnitude of the induced EMF is actually the highest. Because when you apply your Fleming right hand, all the three fingers are actually perpendicular to one another, and we see that the force which is represented by the thumb, it is perpendicular to the index finger. Okay, but as the coil turns and now in position 2, okay, we see that the force, if we need it to continue to turn in a clockwise direction, the force on AB, it is now in this direction. The force on BC and the force on AD is in this direction. And we find that it is now parallel to the direction of the magnetic field, the external magnetic field, which means there is a case whereby your thumb is now parallel to your index finger, right? It's parallel to your index finger. But this has to be so because we need the coil to turn. So we apply the force, okay, which is always perpendicular to the coil. But this force will not be always perpendicular to the external magnetic field. It's only when it's at position 1. Okay, so it's turning, and the force will eventually become parallel to the direction of the external magnetic field as in position 2. So when that happens, there will be no cutting of the external magnetic field because the force is in fact parallel to the external magnetic field. So there's zero cutting. That means zero change in external magnetic field at that moment. So that's why at position 2, the induced EMF is actually 0. But as we continue to turn, okay, and at position 3, whereby the force is actually again perpendicular to the external magnetic field, okay, there is maximum cutting, therefore there will be maximum EMF. But why is it that the EMF now it is in the negative region? It is because just now we talked about it, right? The direction of the current will change every half a revolution. But why does the current change every half a revolution? Because the direction of the induced EMF also changes. It is the one that causes the current to change direction. Okay, then if we go on to 4, if we continue this revolution, turning of the coil in the same direction clockwise, there will again be a point whereby the force is parallel to the external magnetic field. So there's again zero cutting, so again zero EMF. Then at 5, it goes back to its first original position 1. So therefore again we have this maximum. So if we trace it out, it will be a sinusoidal curve. Okay, so let's read the notes. As the coil is rotated through one complete revolution, the induced EMF also moves through one complete cycle of a sinusoidal waveform. The time it takes to complete one cycle is the periodic time t, right? T is the period or the time taken. So the number of revolutions the coil make in 1 second is the frequency. So over here we can ask you for period and also frequency because it's a EMF versus time graph. But you need to know the gradient, don't have to. Okay, so what are some other variations? Like, what if we change the strength of the magnet affecting the EMF output and the period of rotation? So when the strength of the magnet is doubled, okay, the rate of cutting of the magnetic field lines will be doubled because now there will be, can you imagine, there will be twice the number of magnetic field lines to cut. So therefore, instead of cutting one field line, example, now I'm cutting 2. So the rate of change of magnetic field lines is double. Therefore, according to Faraday's law, the induced EMF will be doubled. Okay, but because I'm turning with the same speed, okay, I'm not increasing the speed of rotation. Therefore, the frequency and period will remain unchanged. So as you can see, the period is still t, right? But the magnitude of the EMF is in fact double. Okay, how about we increase or change the number of turns of wires? How will it affect the EMF output and the period of rotation? Now, when the number of turns, let's say it is doubled, then the rate of cutting of the magnetic field lines will also be doubled, and therefore the induced EMF is doubled. But because we continue with the same speed of turning, Therefore, the frequency and period will remain unchanged. So these are popular MCQ questions whereby they give you options such as increasing the strength of the external magnet, or increasing or decreasing the number of turns of the coil. Then choose the correct EMF profile. Okay, so these are very popular MCQ questions, but they can also ask you to sketch. Okay, so the sketching of course is more difficult. So you need to know whether the frequency and period will be affected, and will the EMF also be affected. Okay, what happens if I increase the speed of rotation? Okay, when the speed of rotation is doubled, okay, let's say the strength remains the strength of magnet remains the same. Is the same, and also the number of turns of the coil remains the same, right? Now we are just changing the speed of rotation. How will it affect the EMF output and the period? So when the speed, let's say it is double, the period will be half, right? So this is when it is double in speed. Okay, the period is actually half, because the time that it takes for one complete rotation will be half. Okay, but the rate of cutting of the magnetic flux or the magnetic field lines will be double. Therefore, the EMF is double. Okay. So I have seen questions whereby they change strength of magnet and the change in speed, or they can change all three. Okay, so you need to be very sure what are the effects of changing the strength of magnet, the number of turns, and the doubling in speed. But at the same time, you also need to know why the EMF there is a change. Why isn't it consistently at a certain level? Why does it take on a sinusoidal profile? And why does the direction of the EMF, why does it change? Okay, so these are what you need to know for success criteria C.